We're going to bring up our final speaker now, Anjie Cao. Sorry.
Do I just ignore that? Okay. How do I?
I got it.
Okay.
Oh, do you want to present your
No.
No, you're good?
Yeah. Okay. Yeah, thank you so much for being with me this Saturday morning. And also, hello, people on the internet. I can't really see you or hear you, but I'm with you in some forms. And today I am going to talk about habituation. But before talking about habituation, I want to give a shout out to my wonderful collaborators, Gail, Rebecca, and Mike. Without their help, this work could not have exist in this world. So let's talk about habituation. So I'm going to start by describing a common phenomenon that we have all experienced all the time, which is we make decisions about what to look at and when to stop looking all the time. And let's say that you are a big fan of cat videos like me. And for an entire afternoon, you've been just staring at cat videos. You run into this really cute one and you've been just staring at it over and over and over and over and over again. And what you're actually doing is that at any time point, you're making the decisions of, hey, do I want to keep looking at this really cute cat videos? Or do I want to move on, maybe look at some other really cute cat video like this one? Okay, so these decisions we make all the time. And in fact, this is so prevalent. This is one of the few things that young infants are capable of. So if you're familiar with the infant literature, the ability that infants can make decisions about what to look at and when to stop looking has been used in testing infants' mental capacity. So let's turn to how do people test infants. So in a typical infant looking time paradigms, what happens is actually very similar to the TikTok example I just gave you. So what happened is that young infants will be presented with some stimuli. They will be presented with the same stimuli over and over and over and over again. And their looking time is going to be measured through the process. And what typically people observe is that infants will show a decrease in looking time. And this phenomenon is also called habituation. And at some point, if a new stimulus pops up and people observe what infants do is that they will show an increase in looking time. And this phenomenon is also called dishabituations. So for those of you who are familiar with the developmental literature, you know that this has been the backbone of developmental psychology. But despite the prevalence, the underlying mechanisms behind the rise, what gives rises to this change in looking time actually remains poorly understood. Yeah, this is a little sign. Can I click that thing off? Oh, yeah, I can. Cool. Yeah, so now you can read. So there have been some previous works try to kind of connect certain information theoretic measures with the infant looking behaviors, but they're not necessarily a decision model and they only show correlations. And I'm going to explain what I mean by that. So in those work, a common research strategy is that they will try to teach infants event probabilities. So this is a schematic illustrations from Poli et al. So what infants are going to do is they're going to learn what object is going to pop up in which quadrants. So they teach infants that, and they will also build a kind of ideal learners, which is a model, basically trying to learn the same thing. And then they will be able to drive certain information theoretic measures from the models. So in Poli et al. Case, what they have shown is that they computed a couple of them, including surprisal, entropy, and Kell divergence. And then they will show that these information metrics actually correlates with infants' behaviors. But we all know that correlations are not causations. Just showing the correlations behind those metrics doesn't really tell us what are the mechanisms that give rises to those behaviors. So then we turn our attentions to some of more recent advancements to curiosity-driven reinforcement learning. I'm not an expert in RL, so I'm not going into too many technical details, but the basic ideas of what an RL agent does is that they will have a world model, basically saying that the agent is trying to learn about the world. And then there will be a self model. So the model is trying to make decisions, and the decision's goal is to maximize certain learnings. And the way that they measures the learning in RL is through certain metrics. So one optimal one that people have commonly adopted is called expecting information gain. So it basically says how much information I'm expected to get if I were to do this, if I were to make this decision, take this action next step. And there are other metrics being used, such as KL divergence or surprisal. As you can see, there's some overlaps with the information metrics that people have illustrated correlations with infant behaviors. So with this inspirations in the background, now I'm going to introduce our main model. It's called RANGE. It stands for Rational Action, Noisy Choice for Habituations. And with the remaining time, I'm going to divide my talk into 3 sections. I'm going to first talk about the adult experiment. We are interested in infants, but adults are easy to start. So today we are going to talk about adult only. And then we are going to talk about the model RANGE, and without going into too many technical details. But I'm going to give you a basic intuitions of how our model works. And then, of course, I'm going to show you how our model performs relative to the human behaviors. So first, let's talk about the adult experiment. I hope the media works. Does it work? What does this say? I don't have my glasses. Oh, well, is it telling me to read? Oh my gosh. Okay. Do we have time to do this? I think I give you the access.
It might have gone on my.
Okay, sorry guys for the technical difficulties. We're trying very hard this morning. You know which one it is? Oh, I think it's the other one. Yeah. Just open up the other one too. Okay. Oh, the other one is actually not used in this size.
Perfect. So you can just play it and that's a try. Yep, it's going on.
Okay. Ha. Okay, it works. Cool. Yeah, I'm just going to show you a clip of what our participants saw in the experiment. So this is a self-paced looking time experiment. Basically means that participants are told that they can look at each sequence for as long as they want or as short as they want. At each trial, there will be a creature pops up on the screen. And whenever they're done, they can press a key, go to the next one. And there are kind of different block structures, and between blocks there will be a kind of filler task, and then this is another block. You can see we also manipulate the complexity of the creature, so more complex stimuli will have certain more features on it. If you're curious, we made all of these stimuli in spores because we just want to create something very interesting to look at. Okay, cool. So we run this study on Prolific with 380 participants, and the result I'm going to show you is going to be faceted by the block type. And the no deviant basically means that in that particular block, there's just going to be one creature that shows up over and over and over again. And a deviant basically means that something new will show up in that block. So on the deviant, the 4th trial, it means that on the 4th trial, a different creature will show up, and then the same will occurs at the 5th and the 6th. X-axis is going to be the trial number. Y-axis is going to be the log transformed reaction time, which is basically our proxy for looking time. And we show first that we have habituations, and you can see we also capture a complexity effect. So the red line here are the looking time from the blocks that use complex creatures, and the blue lines are the kind of a looking time from the simple blocks. And we also have dishabituation, which is evidenced by the kind of increase in looking time whenever there's a deviant. You can see the kind of a looking time increase right there. So in summary, this really short, straightforward experiment just showed that we can capture adult habituation, dishabituation, and complexity effect. All of them are kind of a key phenomena in the infant looking time paradigms. And now the main part, RANGE. So as mentioned earlier, we do want to build a decision model. So we assume that our model is constantly making the decisions of, hey, do I want to keep looking at this really stimulus, like kind of like green blob going on? Or do I want to look at maybe something else? And in this case, it might be the cat that's sitting next to your desk. So then we basically in this model represent the stimuli as the binary feature vectors. You can see there's a little under construction line here because we're experimenting with different forms of representations. But in this particular talk, I'm just going to say that all of our stimuli are represented by made-up binary feature vectors. So the one in the vector represent the presence of a feature, and 0 means the absence of a feature. And we assume perception is noisy, and that's why the model needs to take multiple samples from each stimulus. So you can imagine this is kind of like a humans. When you take a first look at something, you didn't see it clearly, so you want to stare at it for longer as you get a clearer sense of what's going on that stimulus. And then we'll be able to use the number of the samples that the model makes to use that as a proxy for looking time. For those of you who are familiar, you might recognize this as a hierarchical beta binomial models, but it basically says that the model will have certain belief distributions over the presence or the absence of certain features, and it will update its belief distributions based on the base rule at each time step. And through this updating process, we'll be able to calculate certain information metrics measures, and then the model will use that to make decisions about when to stop looking. So the way that we are calculating is using a loose choice rule. So you can see here that it's basically calculating our probabilities. The basic intuition is that as your kind of metrics, information theoretics measures from the noisy observation is getting decreasing, your probability of look away is going to get more and more. You're going to be more likely to look away. And this setup allows us to compare multiple information theoretic metrics, including the kind of the optimal case like EIG, or some of the other ones that have been used in the previous literature, such as surprisal and Cal divergence. So this is a model setup. And now I'm going to show you what our results look like. So just a reminder, these are our behavior results. X-axis is a trial number, Y-axis is a log transform looking time in milliseconds. And we show that range are able to capture the looking time pretty good. And you can see that comparing 3 different learning metrics, the fits are actually pretty indistinguishable with one another. They all show pretty comparable fits with only numerical differences. But that actually doesn't tell us what components of a range are really important for the model to work. Because as any modelers, we are making a lot of assumptions about how our model work or how people work, and we make those assumptions into our models. So we do want to examine which assumption that we have made are actually critical for the model's success. So what are the assumptions? First, we are assuming that the model is making sampling decisions based on learning. And second, we are also assuming that perception is noisy. So to examine this assumption, what we did is that we made 2 lesion models, basically saying that, hey, let's throw out that assumption. So one is a no learning model in which the model is just making sampling decision randomly. And the other is a no noise model, which is a model living in a perfect world. Every observation is just a perfect version of the stimulus. And we show that when we threw out those 2 assumptions, our models actually did poorly, suggesting the importance of those 2 assumptions. You can see here that on the second row is the no learning model, third row is the no noise model, and both just didn't produce the habituation, dishabituation, complex effect pattern that we want. And this is pretty much a kind of a work in progress and some of the current directions that we are pursuing. One is that we do want to have a more realistic stimulus representations. As mentioned earlier, here we just represent our stimuli as a binary feature vectors. It's a little bit sketchy and it doesn't have broad generalizability. So at some point, we would like to basically allow the model to learn the embeddings from some of the more recent convolutional neural networks. And then that will allow us to basically learn more about more realistic stimuli, like these really cute, ecologically valid pictures of cats. And second, we are also interested in dissociating the learning policies. So in the current work, we have shown that under current learning context, the 3 learning policies are actually indistinguishable with one another. So for those of you who are familiar, these 3 metrics are actually having very different theoretical underpinnings. But in the current learning context, we actually found that they are pretty indistinguishable. So in the future work, we do want to understand under what kind of setup can we actually dissociate these policies. And finally, I started by talking about infant looking time paradigms, and I want to highlight that we are interested in babies. My wonderful collaborators are working on an infant version of the experiment. Of course, infants are not going to press key on the keyboard. It's just a freewheeling experiment, and we're currently collecting a lot of data from a 8-month-old baby. And we are also interested in understanding the developmental trajectories, which means that we are collecting data from the preschoolers 3 to 5. So it's basically going to be a more colorful version of the adult experiment. And so the data collection is underway. So putting everything together, what have we learned? In sum, we have learned that a decision model like range are capable of producing infant looking time patterns such as habituation, dishabituation, and a complexity effect. And we show that 3 learning policies that have been used, EIG, surprisal, and Cal divergence, are actually indistinguishable from one another, at least in the learning context. And finally, we show that learning and noisy perception are actually pretty critical for our model to work. So with that, I would like to thank my wonderful collaborator again, as well as folks from our lab. If you're interested to read more, the preprint and the code and the data are all available on GitHub. And you can also feel free to reach out to me. I'm always checking my email, and I'm also on Twitter. Thank you so much. Questions? Yeah, please find me.
That's a quick clarification question. Thank you for this talk. Really interesting work. So I guess I was a little confused about the lesion models, and I guess I have just a clarification question about that. So in the case of the model that removes the like perceptual noise, I guess I'm curious about that because I think what enables like any possibility for learning in this model is the fact that there's noise. And so I guess the dissociation between the model without noise, how does it make a choice, I guess, where in that case, it seems like the opportunity for learning should always be 0 because you get an accurate sample just from your first perception. Is that right, or am I misunderstanding?
That's very close to our intuition as well. So basically what this no noise model does is that in the model the model will have certain priors about the model might expect that there's certain noise in the environment, but what it actually getting is very, very like no noise scenario. But we do have we set up a parameter to be like slightly noisy, like very, very minimally, just to keep it numerically stable. But yeah, I agree. So, but you can see here from the curve that it's pretty flat throughout. So it basically destroyed the pattern. I hope that kind of helps. Okay.
Thank you everyone for attending, and thanks for some great talks.